Hello, in this video I'll give a brief introduction to nuclear magnetic resonance, NMR. So, the basic fundamental principle at play here is that atomic nuclei, they have an intrinsic magnetic moment. So most of them have they function like they're tiny little magnets. We call this property spin because the things that we observe act like angular momentum, like if you spun a top. And it does a lot of things that look just like angular momentum. But remember, nuclei aren't actually spinning. They are both particles and waves because they're on that length scale where particle-wave duality actually matters. And, it's a little iffy to say that they spin. But hey, that's what everybody says. We're going to go with it. Nuclei have a property called spin. But not all nuclei, most nuclei have a property called spin. And so the spin can take several values. Some nuclei have spin 0, which means they don't do anything with NMR. They don't have this intrinsic magnetic moment. But most nuclei do. It can take several values, either integer or half-integer values. The ones that have spin equals 1/2 are by far the most useful for magnetic resonance. Now, if this sounds kind of familiar, it's because in general chemistry, when you were filling out electron configurations, your last quantum number was m sub s, the spin quantum number for the electron. And the electron could take two values, plus or minus 1/2. Now, that's the same physical property that we're dealing with here. Electrons are spin 1/2 particles. You can do magnetic resonance on electrons. It's called electron spin resonance or electron paramagnetic resonance. But here we're focusing on the nuclei, and nuclei can take spin 1/2 or they can take other spin values. So let's look at that actually. So here's a periodic table that shows by color the spin value for the most prevalent magnetically active or NMR active nucleus. And so of note, hydrogen, most hydrogen is hydrogen 1, which means it's just a proton, no neutron. 99.98% of it is. And this is an amazing isotope for doing NMR. It's spin 1/2. It works really well for NMR. It's the basis of all kinds of stuff we do in chemistry. It's the basis of MRI. All MRI pretty much is looking at the hydrogen spin. We call it proton NMR or proton MRI because, well, hydrogen 1 really is just a proton. Now, hydrogen 2 is called deuterium. It has a proton and a neutron in the nucleus. And that is NMR active. It's spin 1. Its frequency is different than hydrogen 1, so you wouldn't see it at the same time. And we use deuterium a lot, not because we want to observe it, but because we don't want to observe it. So you'll put your analyte into a solvent where the solvent molecules have deuterium instead of hydrogen so that we don't see them in the NMR measurement. You see a little bit of it, but if you didn't have deuterated solvent, you'd see this giant, huge peak from your solvent, and you wouldn't be able to see your analyte at all. So that's often what we use deuterium for with NMR. Carbon is both useful and frustrating. So 99% of carbon is carbon 12, 6 protons, 6 neutrons, and that has no nuclear spin value. Like, it doesn't do anything with NMR. Carbon 13 is 1% of all carbon, naturally, and that's super useful for NMR, which is great. But the problem is you're only looking at 1% of all the carbon in your sample. It's kind of insensitive. So it's frustrating in that way, but when you can get the spectrum, it's a super useful spectrum to have. Nitrogen would be useful because many organic molecules contain nitrogen. Nitrogen 14 is spin 1 in a horrible NMR nucleus, and unfortunately most nitrogen is nitrogen 14. Nitrogen 15 is useful, it's spin 1/2, but it's only 0.4%, and it's kind of hard to deal with in terms of the really low natural abundance. So you can do nitrogen NMR, people do, it's just kind of a pain. Other nuclei on here I can just briefly mention. Fluorine works really well for NMR, so does phosphorus. Oxygen, unfortunately, there's only a tiny fraction of oxygen atoms that have a spin value, and it's spin 5/2, and it's pretty useless. So people don't really do oxygen NMR. And there's a bunch of other nuclei in here as well that can work better or worse for NMR, depending on what you're trying to do. Cool. So let's continue with NMR theory. How does this work and why does this work? Okay, so like many other things that are on the small length scale, you can think of NMR either with a quantum mechanical picture or with a classical physics picture. And you are describing the same thing. It's NMRs on a size scale that's kind of in this fuzzy zone between quantum and classical, and you can use either one. So I'll start with the quantum version. So in the quantum version, these nuclear spin states are quantized. We're talking about spin 1/2 nuclei here, so there's two states, up and down, or spin 1/2 and spin minus 1/2. Like a spin 1 particle would have 3 spin states, but we're not going to go there. And the energies of nuclei in these different states are equal if you're not in a magnetic field. But if you're in a magnetic field, then the energy states are different, which is why we put our samples into these giant magnets. And I'm not talking refrigerator magnets, I'm talking magnets that could knock your refrigerator over, like big old magnets. Okay, so we put our sample in the magnetic field, and the nuclei occupy one of these two states. Now, the Boltzmann distribution is a mathematical thing you can do that tells you about the relative populations of nuclei in these two energy levels, and it ultimately tells us the populations are pretty much the same, which is unfortunate because NMR only really is functional on the nuclei that don't have a friend in the upper energy state, which is kind of a bummer. So NMR is a pretty insensitive method, even for hydrogen 1, compared to other analytical techniques because of this problem. But it still works. So in the quantum picture, you'd apply a bit of energy at delta E. Well, really at the frequency that's equal to delta E. So you apply a pulse of energy with the frequency that then corresponds to delta E. And you promote a nucleus from the lower energy state to the upper energy state. And then you wait a little while because the relaxation's not instant here. But then it happens and the nuclei relaxes back down to the lower energy state and emits energy as a photon that you can detect. The relaxation here is not instant compared to many other spectroscopic techniques we do, and that affects how fast you can take NMR spectrum. You have to wait for it to relax before you can really go again, so that's an important thing to keep in mind. Now, what makes this useful for chemistry is that variations in chemical environment, the nuclei, say, on an aromatic ring versus the nuclei in a CH2 group, those sit in different environments and have slightly different delta E's, such that they'll emit photons of slightly different energy, and you can detect that and get lots of information about structure. And that's what gives NMR so much power. Okay, so let's work on the classical version now. In the classical version, nuclei behave like tiny little magnets, which we've kind of said before, right? They also behave like little spinning tops because they have angular momentum. So, think about the magnetic aspect. First of all, you have a giant sample because even a little bit of liquid has a ton of molecules in it. So if you sum up the magnetic moments of all these little tiny magnets, you get the net magnetic moment. And this net magnetic moment aligns with the external magnetic field, which is kind of how things behave. Like magnets will line up with each other. And so we write B subscript 0 for magnetic field. B is what NMR people use for magnetic field most of the time. And we'll call this B0 or B0. It's the giant magnetic field you put your sample in. And your nuclei, when you average them all together, on average, they're pointing in a way that's aligned with this magnetic field. So the next part that we're going to talk about requires a little bit of physics background, so let me give you that. So if you have a magnetic moment and an applied magnetic field, if they are perpendicular to each other, they will experience a torque. The right-hand rule tells you this. You hold your fingers out in the special right-hand rule way. Your index and your middle finger are the magnetic moment and the magnetic field, and your thumb is the torque. Okay, so right now as it's sitting, there's no torque because they're perpendicular to each other, so we don't get a cross product. But we take advantage of this behavior and kind of purposefully apply a pulse of electromagnetic radiation that will move this around. So remember, electromagnetic radiation has both an electric and a magnetic component. Let me redraw this little picture. So if you put in electromagnetic radiation at a frequency that happens to match the frequency from delta E in the quantum version, then you'll move this net magnetic moment. So really this should go into the page for the right-hand rule to work, but I'm going to draw it to the side just so that it's easier to see. Okay, so you apply this little magnetic field. It's going to cause your net magnetic moment to rotate, and then you turn it off when it rotates about halfway around, or I should say rotates about 90 degrees. And then you observe what happens. So what happens with this is that the main magnetic field takes its turn. It exerts a force onto the net magnetic moment that causes it to rotate around. This rotation is called precession. It looks just like a top when you spin it, how it kind of wobbles around its central axis. It kind of looks like that. It precesses its way back up to where it started. It happens to rotate at this frequency. This is called the Larmor frequency. It's the same frequency for the quantum version. And great. So this is rotating around. Now, if you put a loop of wire around this, or several loops of wire around this, the rotating magnet, that is the net magnetic moment, will induce a current into this coil, just like the rotating magnet inside an electric generator will do. And so this generates a little current into the coil. It oscillates, it's spinning back and forth, so it's an AC current. And this thing is called the free induction decay. So free, because it's free to spin. Induction, because it induces the current into the coil. And decay, well, let's talk about the decay. So let me scoot this up a little bit. Okay. So the free induction decay looks something like this. You're measuring the voltage as it alternates, right, with your alternating current. And over time, the signal you record kind of decreases in a somewhat exponential fashion. And so that's the free induction decay. Now, the relaxation piece is this, that the rotating net magnetic moment will eventually work its way back to equilibrium. And so it kind of spins around and around and around and all the way back up. Then let me erase this and put it back the way it was. So it goes back to equilibrium. This takes some time. And analogous to the quantum version, we have to wait for the relaxation to occur before we can go again. If you don't wait for it to occur, you apply another pulse, you're going to spin this thing all around in crazy ways, and you won't get as good of signal out of it. Okay, so then how do we get the chemical information? Just like the quantum version, little variations in chemical environment will give us variations in this oscillation frequency, and that's great. Because if we have another oscillation frequency kind of superimposed on our original one, the math we do later on this allows us to unsuperimpose these and see them as different peaks in our spectrum. So, okay, that's the theory bit. Quantum, classical, they both work. We usually treat this classically because that's how we actually acquire the information. We acquire it as this free induction decay. It's what we do. Cool, so let's talk about what we do in an NMR experiment. So the first thing we do is we send in this pulse of electromagnetic radiation that tips the net magnetic moment 90 degrees over. And this pulse is just a little short burst of the electromagnetic radiation. For most NMR, this is in the radio frequency range. The 9.4 Tesla magnet that we have at our school, for hydrogen nuclei, this is 400 megahertz. For carbon, it's about 100 megahertz. That's the frequencies they are. There's a math equation that can tell you what the frequency is, given a constant for each nuclei. Okay, so we send in this little bit of radio frequency energy, and then, again, we put just enough in to rotate it down to about 90 degrees. You can also intentionally rotate it a little less than 90 degrees so it relaxes faster and you can repeat faster, but we'll ignore that for now because that complicates things. This is a parameter that you adjust, right? What amount of energy you need to put in to tip the nuclei just down 90 degrees. And so we'll talk about that in a minute. Okay, and then you wait a tiny bit of time for the giant pulse to work its way out of your electronics. It's about 6 to 10 microseconds or so. And then you can observe the FID. And you want to make sure that you observe the whole thing. This is called the acquisition length. And you want to get the whole FID because the math that we do on it, the Fourier transform that I'll talk about on the next slide, the math we do on it gives you really funky results if you don't acquire the entire thing. Okay, another thing to keep in mind, right, and I've talked about relaxation a number of times, is we have to give a break in the experiment for this relaxation to occur, so we call this the repetition delay. All right, since I'm making this video for a class, and in the lab part of this class, we're going to adjust these parameters, let me reference them here. So in the Bruker topspin software, The repetition delay in most experiments is D1, D for delay, 1 because it's the first and only one that we specify. The pulse is P for pulse, and in this experiment there's only one, so it's P1. There are other NMR experiments that use a whole bunch of pulses, but here we just have one. And then AQ is the acquisition length, and that's just a value you specify in a number of seconds. The pulse is in microseconds, the repetition delay is in seconds. Okay, so observing the FID is great and all, but how do we go from the FID to a spectrum? Okay, so here's my picture of the FID that I drew, and assuming we have hydrogen nuclei in our magnet at our school, these are oscillating at about 400 megahertz. Now we take the data from the FID and do something called a Fourier transform on it. It's math that's built into the software, you don't have to worry about it, you just type the buttons to make it happen, and it does this transform for you. And so if your signal's oscillating at 400 megahertz, you'll see a peak at 400 megahertz, and now the x-axis is frequency. So this tells you at what frequency are things oscillating in your FID. And if you have more than one thing in your FID, you'll get a second peak in your spectrum, right? So say this blue line is oscillating at a slightly different frequency, you'll get a peak at a different spot in your spectrum, and that's what you'll see for your spectrum. Now, it is frequency. We define it in NMR as frequency difference from a reference in parts per million, and give it this little lowercase delta and call it ppm as our x-axis. But it's essentially frequency. It gives us that information. And the wealth of information that we have from an NMR spectrum is part of the power of this method, that we can get all kinds of useful information about our compounds from NMR, and it's a wonderful thing to do. So hopefully this video was helpful in giving you the basics of NMR, and happy sciencing, everyone.